Yep, that's true.
Like I know two of them. Right? Pi and E.
Okay.
Those don't count.
So the next thing that that I want to do is to count regions in hyperplane arrangements. You know that if you have a combinatorialist in front of you, he's going to be counting things. So that's what it's going to be. So we're going to count regions in hyperplane arrangements. And we did this last time for one example, which was the braid arrangement. So we saw that the number of regions of the braid arrangement is n factorial. But today I want to discuss how you can count regions of arbitrary arrangements, basically. Well, today they're not going to be so arbitrary. And I'm going to start with an example. Let's consider the arrangement Gn, where you have n lines in the plane in general position. Okay. Now, what does general position mean? What would you say? So probably no parallel lines. No two parallel lines. No three meet on a line or concurrent. I also heard somebody say no two perpendicular, which I agree that if you choose general lines, they're not going to be perpendicular. But it turns out that actually we don't care. It's fine for us if they're perpendicular. Remember that I told you general is kind of a choose your own adventure definition. Depending on what you choose, you get to prove different theorems. And for what we're going to prove, this is what we need. It might be that if you're trying to prove something different about lines, or about random lines in the plane, then you're going to need something different. But right now, general is going to mean this for us. Okay. So I take some lines in the plane, like this. Okay. And I want to count the number of regions. Okay. So R of Gn is the number of regions. So in this case, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 regions. Okay, so and these are four generic lines in the plane. So I said 11, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so how can we do this? Well, there's different ways that you could try to do this, but what I'm going to do is try to figure out what this number is recursively. Okay, so suppose that I already know what R of Gn is. Okay, so I know how many regions are created by n lines, and now let's figure it out for R of Gn plus 1. And so what I'm going to do is first draw n lines, and then I'm going to draw an n plus first line. Okay. So here we add a line. Okay. So I'm just going to add some line to this picture, and it doesn't matter where I do it as long as it's not parallel to any of these lines and it doesn't go through any of the points of intersection. So maybe I'll draw this one. Okay. And the point is that the regions of this new arrangement are related to the ones of the old one, right? So what you can say is, well, first, how many regions did I have? Number of regions I had. And then I should add something. So what should I add? Well, basically, some of the regions that I had before are now being split in two, right? Like this region is split in two, this region is split in two, and so on. And so whenever a region is split in two, then I should put a +1 in my count of number of regions. So I should have plus number of regions I had which are cut in two by this new line. Okay? So for example, according to this, I had 11 regions, and now how many of those regions are cut in two? 5, let's see them. They are this one, 1, this one, 2, this one, 3, this one, 4, and this one, 5. So let's compute these two numbers. So how many regions did I have before? Well, that's R of Gn, right? Okay. Another question is how many regions did I create by doing this? Okay. And the point is basically that if you look at the points of intersection of the old lines with the new line, how many pieces do I create on this blue line? Well, I had n lines, which means that I have n blue points, right? And there I'm using that I don't have parallel lines. So every other line is going to hit this one in exactly one different point. So I'm going to get exactly n blue points on this line. And so that means that this is going to be split into n+1 segments, right? n+1 pieces on blue line. Right? Here you have it 1, 2, 3, 4, and 5 pieces. And clearly, each one of those pieces is cutting a region in half. Okay? And so that means that this is exactly n+1. Do we agree? And through this recursion, you can figure out what this number is. It's not hard. And I'll tell you what the answer is. I mean, you see that basically when you add the n plus first line, you get a plus n+1. So then this is going to be n plus r of gn minus 1. And then r of gn minus 1 is n minus 1 plus r of gn minus 2. So if you kind of do this a bunch of times, you're going to get n plus 1 plus n minus 1 plus dot, 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 dot. So it's going to be something like a triangular number. Okay? You just have to be a little bit careful. And what you get in the end is this. There's different ways of writing it, but this is a way that I like. Okay? And clearly you can prove this by induction, right? I mean, if you have this recursion, you can prove this by induction. So for example, for 4, we get 4 choose 2 is 6, plus 4, 10, plus 1, 11. So that's correct. Okay? So this is just by a straightforward induction. Now remember we talked about counting not only the regions, but also the bounded regions. Okay, so how many bounded regions did G4 have? If you can ignore that blue line that I drew, then you see that I have 3 bounded regions. Okay? How many new bounded regions do I create with this blue line? The point is that when you look at these 5 blue segments that created new regions, the 2 on the ends, they're infinite segments, and so they can't really be bounding anything finite. But these guys are always cutting off a new bounded region. Each one of these finite pieces is always cutting off a new bounded region. And so the number of bounded pieces that you're going to get is m plus 1 minus 2. Okay. So by a similar argument, you get this. Similarly, and then through induction, you're going to find that the number of bounded regions is n choose 2 minus n plus 1. Okay? Okay. Now there's something here that I hope surprises you, which is that these numbers minus n plus 1, yeah. So one thing you'll notice is that by proving this, I'm also proving that these numbers don't really depend on where the lines are, right? Which is actually not so obvious. And it might be a little bit clearer for the number of regions, but not for the bounded regions. And let me show you an example of why that's a little bit surprising, if I can. So, for example, so this was my previous situation, right? But now let's take instead a different blue line, like this one, for example. Okay. So then you see that these pictures are different from each other combinatorially. And they don't really look the same, right? For example, here all the bounded regions are kind of in this V-shaped thing, whereas the bounded regions here are not contained in any V-shaped thing. Yeah? So the way that the bounded regions are arranged around each other is different, and yet the number of regions is the same. Okay? And that's a nice consequence of this proof. So all I need is no 2 parallel, no 3 concurrent. I don't need anything else. Okay? And now you see why, for example, I don't care if they're perpendicular. As long as the things are intersecting, that's all I care about. So this one has 6 bounded regions. But this is G5. And this one also has 6 bounded regions once you add the blue one. Thanks for checking. So let me point to them. But so here's 1, 2, 3, 4, 5, 6. And here it's 1, 2, 3, 4, 5, 6. So actually there's this, probably the main textbook is on this topic is called Arrangement of Hyperplanes, and the introduction talks about the problem that started it all, and it's kind of a goofy problem, and that's the one that we're going to do next, which is if you have a block of cheese and you're going to make n cuts on this block of cheese, then how many regions, how many pieces of cheese can you make? Okay, that's it's a little embarrassing when that's the problem that starts your whole field. But it's true. I mean, apparently that was the first kind of problem in hyperplane arrangements other than 2-dimensional things. Okay. So let's do that example next. Okay. N planes.
There's like a ham sandwich now too, right?
I don't know that one.
You could always slice it wholesale to the hyperplane.
Oh,
so
yeah, yeah.
exactly half of everything's on each side.
That's right. That's right. So M-planes in R3. What is the largest number of regions that you could have? Now, of course, the cheese doesn't really matter, right? It's really about this space. M-planes in R3. How many regions can you form? One thing you should notice is that I could have also asked that question here. I mean, I could have phrased things a little bit different, and I could have said, if I give you n lines in the plane, how many regions can they make? And then you would tell me, well, if you want to make a lot of regions, then clearly you want to avoid parallel lines because you're wasting regions by doing that, right? If you take two parallel lines, and if you force them to intersect, you're going to make more regions. Or if you have three concurrent lines, then by moving one a little bit, you're going to create another region. So these are the kinds of things that you want to avoid if you want to make a lot of regions. Okay, and so that's the same thing that I want to do here. General position. So let's talk about what general position means in R3. What should I avoid? You don't want what?
Cheese with holes in it.
Yeah, I should have said this cheese doesn't have holes in it.
Well, no parallel planes, obviously, but you don't want.
No parallel planes.
You don't want a unique solution to the intersection of three or more planes.
No two parallel. What else? So how can you say that geometrically?
Well, you don't want them to. You don't want three or more planes intersecting in a line.
So you don't want three intersecting in a line? Because if they intersect in a line, then by tweaking one of them, you can make more. Three intersect in a line. Because if they intersect in a line, then if you move one of them a little bit, let me. This is hard to draw, but I'm going to try anyway. So if you have three intersecting in a line, then you have something like this, right? And that's creating 6 regions. But you see, if you tweak one of them just a tiny bit, then you're going to have 3 planes intersecting in a point, and that's just going to look like the orthents, and it's going to have 8 regions. Okay, so if this has 6 regions, this has 6 regions, but then by tweaking it, you get it to look like the coordinate planes. This is harder to draw than it should be, but hopefully you can kind of see that. Okay, 8 regions. So this is why you want to avoid three in a line, because if you have that, you can tweak a little bit and make more regions. Anything else you want to avoid?
We also don't want pairs intersecting in parallel lines.
You don't want pairs intersecting in parallel lines.
Like if you only slid the diagram that you had drawn before, so it had sort of a cross section that we did allow, but that everything was parallel from there on out.
So yeah, I think that's going to matter. Another thing you want is no 4 intersecting on a point. So basically, what you want is that what you want basically is that if you take any 3 of the hyperplanes, they intersect in a unique point. Okay, that's it. The dimension of, or rather, hi intersect hj intersect hk should always be a point. Okay. If you have that condition, then the following argument is going to work. I'm going to make kind of the same argument. I'm going to say, okay, well, suppose that I know it for hn, and let me add another hyperplane, hn plus 1. So how many regions does this have? Well, I make exactly the same argument. The number of regions in Hn plus the number of regions of Hn cut in two by the new hyperplane. Same argument. Okay. So let me try to draw a picture here. Here you have a bunch of planes, and you shouldn't think that you should be able to see this picture. You just have a bunch of planes. Okay. And then I add a new plane. And so here's my new plane, and let me that's the new plane. Okay. And so what does the situation look like now? The number of regions you had is this. Now, how many new regions are you creating? Well, if you look at what happens inside this plane has kind of shadows of all the other planes. It has intersections of all the other planes. Yeah? So, I don't know, if here I had 1, 2, 3, and 4 black planes, then each one of those planes is going to intersect this blue plane in a line, right? 1, 2, 3, and 4. And then what? Well, you notice that, for example, this region right here looks like what? It's a slice of a region that you cut. You had a. I mean, this is just some region in here. It's hard to see, but there's one side and another side, and those two sides were the same region, and now you cut them into two. Okay, and so the number of new regions you created is exactly the number of regions you have in this picture. Exactly. It's like this blue plane has a positive and a negative side, and for each region that you create in this blue plane, that has a positive and a negative region there, and that positive and that negative region were the same region when you didn't have the blue plane, and now there are different regions when you add this blue plane. So that's exactly the number of regions you create is the number of regions that you have here. How many is that? It's exactly what we just did, right? So here you have n lines. And then the number of regions that you created here is n choose 2 plus n plus 1. Okay. And again, by a similar argument, you can show that the number of bounded regions, and actually this was part of the cheese problem, is how many regions don't have any of the what's the word for the rind. How many of the pieces don't have a part of the rind? Well, you can arrange so that they're precisely the bounded regions. I mean, if the cheese is big enough, then it contains all the bounded regions, right? And so the number of regions that don't contain any of the rind is precisely the number of bounded regions, which is the old number of bounded regions plus the bounded regions in this picture, which is n choose 2 minus n plus 1. Okay? And again, through a straightforward induction, you can then prove the formulas for this. So these are the recursive formulas. And then the formula that is not recursive looks like this. Okay? The number of regions of created by n planes in general position is n choose 3 plus n choose 2 plus n plus 1. And the number of bounded regions, would you like to venture a guess? Just for aesthetic reasons, you might hope that something is the answer. Minus n choose 2 plus n minus 1.
Is that true?
It's true.
That's what I want to be true.
It's what you want to be true, and it is true. Okay. And you'll have no trouble proving it from this. It's, yeah. Okay, so I think those are very nice answers, and this must be true in any dimension, right? I mean, this could not possibly be the end of it. So it must be that if you have a d-dimensional cheese, then you know exactly how many regions there are. It's n choose d plus n choose d minus 1 plus and so on. And so that's where we want to head next. We want to be able to prove a statement like that. I mean, really, if you do this in d dimensions, you're going to get exactly the proof, the d-dimensional result of this. Okay. Okay. So let's make some definitions that are motivated by this. So let's say that you have a hyperplane arrangement. Okay? Then I'm going to define two things. So the deletion is going, so I should say let's consider a hyperplane arrangement, and let's consider one of the hyperplanes. Okay. So the deletion is just going to be, so we denoted A minus H1, and it's just basically all the other hyperplanes. Okay. In RD. So maybe we'll do an example here. So there's an arrangement, and it has, here's H1, here's H2, or let's make this H1, H2, H3, and H4. In R3. And then the deletion is what you get when you just forget about one and you draw the other ones. Okay? Now, you should realize that I'm drawing these hyperplanes like this, but all of these hyperplanes are infinite in every direction, right? So, I mean, I draw it like this so we can see the picture, but really, this goes on, this goes on, this goes on. Like this. And so on, right? Everything extends in all directions. And so in particular, this picture is exactly the same as that picture that I have over there of three planes that intersect in a line. And they form 6 regions. So that's the deleted arrangement. But the point that I want to make with this is that we are thinking of this one as being the blue hyperplane in our previous pictures over there. So And then I would also like to create that other arrangement that I have over there, which is called the contraction. And it's basically what happens inside the blue plane. Okay? So the blue plane looks like this. And I'm just going to look at what the other planes look like when you only restrict the blue plane. Okay? So you see that, you know, if you live in the blue plane and all you can see is the blue plane, then 3 looks to you like just this line here. Okay, so 3 looks like this. 2 looks like this. And 1 looks like this. Right? No. You live in 1, so 4 looks like this. Okay? So all I'm doing is considering the intersections of every one of the hyperplanes with that special hyperplane H1, and I'm calling that the contraction. So contraction, denoted like this, and is what you obtain by intersecting each one of the other hyperplanes with H1. Okay? Now, because you intersected everything with H1, that means that these things live inside H1, right? And H1 is a hyperplane, so this is, H1 is like r to the d minus 1, right? And now, what happens if you intersect two hyperplanes? What do you obtain? So this hyperplane is d minus 1 dimensional, this one is d minus 1 dimensional. When you intersect them, their intersection is going to be d minus 2 dimensional, because you're basically, one hyperplane is one equation, and so if you have two equations, that drops your dimension down by 2. So it should be a d minus 2 dimensional thing. What's the exception to this? If they're parallel, then the intersection is empty. Or if they're the same, then the intersection is full dimensional. And so you want to make sure that H1 is not repeated here. So let's say that here, not repeated in A. And as long as it's not repeated, then each one of these things is a d minus 2 dimensional plane in d minus 1 dimensional. So it's a hyperplane. Okay? So this is going to be a hyperplane arrangement, but in 1 dimension lower. And you see it here. We had a 3-dimensional hyperplane arrangement. Now the deletion is 3-dimensional and the contraction is 2-dimensional. So that's always how it is. That here you have planes in R3, planes in R3, lines in R2. And that's always like that. So that always drops in dimension. Okay? And proposition, basically if you want to count the number of regions of your arrangement, A, you can use this kind of blue plane method. Okay? You can say, well, if I want to count the regions of this arrangement, then let's take out the blue plane and let's count the regions in here. Okay. And again, I'm going to write the proposition and the proof at the same time. So the number of new regions is equal to the number of old regions plus the number of old regions that are cut into by H. But again, the same argument holds that when you bring in this new hyperplane, how can that new hyperplane cut a region in two? It's precisely because you have a region of this contraction that separates two pieces, the top piece and the bottom piece of a region. Okay? So for example, if you look at this region of the contraction that's living right here, and this is as you can see, when you go from here to here, when you insert the blue plane, then you had a whole region that is now being cut by this red thing into two regions. Okay? And so by the same argument as before, we get this. Okay? And almost the same is true for the bounded regions. So let me say what happens for bounded regions. So there's two cases. Let's see, what's the best way to explain this? Maybe let's explain this with an example. No, so arrangements might or might not have bounded regions. I'm trying to think of what's a good example that I can actually draw. Maybe let me tell you what the conditions are. So let me make a definition that the rank. So if you have an arrangement A, this is an arrangement in. Let's give it names. So A is H1 up to Hn in Rd. And let's say that you have some subset of A. Then I'm going to define the rank of B to be D minus the dimension of the intersection of the hyperplanes in B. So let's see what this means. So maybe let's do it for this example. So what is the rank of H1? So H1 is the blue plane. So it's D minus the dimension of H1. So D is 3, and the dimension of H1 is 2. Right? D is 3 because we live in 3 dimensions, and each hyperplane is 2-dimensional, so we get 3 minus 2, which is 1. And you see, actually, this is true for any of the hyperplanes, not just for H1. Okay. What is the rank of Hi and Hj? It's 3 minus the dimension of the intersection of I and j, Hi and Hj. Now, if you look at this picture, you'll see that no matter what two hyperplanes, they all intersect in a line. Any two intersect in a line. So that means that here we have 3 minus 1, which is equal to 2. Okay? Okay, so when is this going to get interesting? What about the rank of hi, hj, hk? So this is 3 minus the dimension of the intersection of hi, hj, and hk. Okay? And now you see that actually it's not so obvious. I mean, it's not so immediate. Because, for example, if we did it for 2, 3, and 4, then 2, 3, and 4 intersect in a line. Okay? And so that means that here I get 3 minus 1, which is equal to 2. Okay? 3 minus 1. But if we took the rank of any other hi, hj, and hk, so as long as I, j, k is not 2, 3, and 4, then any other 3 of the hyperplanes intersect in a point, and so I get 3 minus 0, which is 3. Okay? So you see that the rank is basically telling you kind of how degenerate things are. Okay? The point is that 2, 3, and 4 they're dependent in a sense, which is why they don't. I mean, this is really like the rank function in linear algebra, right? So a single hyperplane has rank 1, 2 of them have rank 2, 3 of them have rank 3, unless they're dependent like this. Okay, and really, this is very precise because this is the dimension of the span of the normal vectors. So if we say that hi has equation ai dot x equals bi, then this is the dimension of the span of the ai's where ai, let's say hi is in B. Okay? You see, if you look at the normal vectors of these 3 vectors, of these 3 hyperplanes, the normal vectors 2, 3, and 4, then they're all on this they're all on a plane, right? They're all on a horizontal plane. And so even though there's 3 of them, their span has dimension 2. And so that's why the rank here is 2. Okay? Okay. Okay, so all of that goes, I say all of that because this equation applies if the rank of A minus H equals the rank of A. But if that's not true, then you get no bounded regions. And okay. I think I can even draw an example for you of why this matters. Let me add another hyperplane to this picture that looks like this. I'm going to draw it in a different color so we don't get it confused. So let's draw this hyperplane here. Let's call it 5. Okay? So then here it looks like this. Okay, here's 5. And here, it looks like this. Now, how many bounded regions do we have in each one of these? So, well, this guy has 2 bounded regions, right? 2 bounded regions. How many bounded regions does this have? It doesn't really have any, right? Because you have this whole lineality space. So you can't, you have no way of vertically bounding anything. So here you have 0. And what about here? Zero also, because you have one horizontal thing and everything else is this lineality space. So the regions above the blue plane are unbounded on the top, and the regions below are unbounded on bottom. Okay. So here you see an example where you don't get that this is this plus this. And why is that? Well, it's because we have, for example, this region. According to the argument we would like to make, this bounded region is cutting one of these regions into 2, and one of which is bounded. Okay, but the problem is that here, when we look at the 2 regions bound by this guy, okay, so the arrangement looks like this now, and you see that both of these regions are unbounded. Okay, but you see it's very special that they're unbounded because everything has to line up with this lineality space for both things to be unbounded. If you don't have lineality, then either one or the other is going to close down. Okay, and so that means that this argument works unless you have precisely the situation where you have everything having a common lineality space and only one plane that is splitting it into 2. Okay, that's the basic idea. You can work out the details. You'll see that this is exactly what you need. But that's the theorem. Okay. Now, and I should tell you, by the way, that when you actually do computations, this is generally this is what happens, and this happens only in kind of strange cases. Okay. But generally, you just think that both regions and bounded regions have this recursive property. Okay. Now, there's one important thing that you should understand about these 2 operations of deletion and contraction. They're very, very important, and these are generally the tools that allow you to do inductive arguments for hyperplane arrangements. Okay. So if you ever want to prove something about hyperplane arrangements and you want to prove it by induction, then generally what you do is you say, okay, well, if I want to prove a statement for A, then I prove it for the deletion and the contraction recursively, and then I piece that together like this. And this is an example of such a thing. If you know the regions of the deletion and the contraction, then you know the number of regions of the arrangement. Okay? Okay. So let's do a last example of this. Which in my notes I called A n of D, and these are n hyperplanes in general position. Okay. And what does general position mean? It means that the rank of a hyperplane is 1, the rank of 2 hyperplanes is 2, the rank of 3 hyperplanes is 3, and so on. Okay? So the rank of B hyperplanes is basically B or D if you kind of run out of space, because the rank has to be between 0 and D because the dimension is between 0 and D. So what's the point? The point is that if you want to compute the number of regions of this arrangement, you can do it by deletion contraction. So you delete a hyperplane and you contract that hyperplane. Okay. Now, what happens when you have this and you delete one hyperplane? Well, what you're going to get is now how many hyperplanes? N minus 1. And what dimension? D. Right? Plus. What happens when you take n hyperplanes in d dimensions and you intersect with a hyperplane? Then basically you're going to get how many hyperplanes? N minus 1, but they now live in a dimension lower, in dimension d minus 1. Okay. And so then this allows me to prove by induction this formula that the number of regions is n choose d plus dot 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 plus n choose 0. How do I do it? Well, I basically have this tool that allows me to do it by induction. So this first thing is n minus 1 choose d plus n minus 1 choose d minus 1 plus dot 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 plus n minus 1 choose 1 plus n minus 1 choose 0. This one, I get n minus 1 choose d minus 1, n minus 1 choose d minus 2, up to n minus 1 choose 0. And then Pascal's triangle precisely tells you that, or whatever you prefer to call this plus this is equal to this. This plus this is n choose d. This plus this is n choose d minus 1. This plus this is n choose 1. And this plus this is n choose 0. Okay. And so that shows you that the number of regions of our generic arrangement in d dimensions is given by this, and by the same argument, the number of bounded regions is n choose d minus n choose d minus 1 plus n choose d minus 2, etc.